but we can start our medallion lecture. The medallion lecture will be delivered by Vlada Limic. She received her undergraduate degree in mathematics from the University of Zagreb in 1994, PhD from the University of California at Berkeley in 1998. In the, of course, usual career, postdocs and so on. In 2006, she joined the CNRS in France, and starting 2017, her affiliation is the mathematics department at the University of Strasbourg. Most of Vlada's research is either on coalescent processes or on models with reinforcement. She was a recipient of the Alfred P. Sloan Research Fellowship in 2005, and she got the Friedrich Wilhelm Bessel Research Award from the Alexander von Humboldt Foundation in 2016. I am pleased to hand in remotely the medal to Vlada. Congratulations on this prize award. I hope we shall enjoy with less adventures the rest of the lecture. Of course, you will get the medal from IMS probably by post or by some occasions.
Well, thank you very much for the introduction. I'm very sorry that you know, we went through these difficulties. I really didn't expect them. Of course, everything would have been easier if I were there, but then something else would have gone wrong, perhaps.
Thank you.
And I really appreciate, it's a great honor. It is my first and possibly only IMS prize. I'm very grateful to the community reconnaître is the word that comes to me, to recognize, to recognize my efforts as a mathematician. You know, I hope you enjoy the rest of this lecture. There was a certain amount of time, thought and energy that went into it. You will see, I hope, although it looks a bit like a cartoon, there is some, I hope you enjoyed and learned from it, as I promised in one of the abstracts that I sent to either IMS Bulletin or the Think to the IMS Bulletin. So now what is worrying me is that Zoom tells me that votre partage d'écran est en pause. For some reason, something has paused, and I'm trying to hit the green button that says retake the screen sharing, but let's see if you see the second screen. No, you don't see it. So it's truly unpaused. So I'm switching between the pages and it doesn't work. So maybe for the third time I enter the...
No. I think just to withdraw the screen and then try to again. I mean,
arrêter le partage, okay, and
okay,
then try again.
Try again.
Okay.
And then,
Acrobat Reader.
This would be too long journey. Oh, perfect. Now it's perfect. Perfect. So let me tell. The title is Multiplicative Coalescent Related Processes.
Okay.
The podium or the screen is yours.
Thank you very much. So I have 10 minutes less, and I will take you on a journey, mostly in pictures. This is, as most of you know, and the model that I'm going to recall here is something that is going to be recalled again and again. It has been recalled the day before yesterday, today, and tomorrow. It is one of the key models that people study in the it is the key model in random graphs and networks. And when I went to some talks yesterday and the day before, the phase transition that people were interested was the one of connectivity. In this talk, it's going to be a different phase transition, but emanating from the same seminal works by Erdos and Reni. And it is the phase transition, I don't know if you see my cursor, but of the giant component.
Sure.
So there is this smaller critical parameter. So the model is the same, n vertices, n is going to infinity. There is a parameter p for the independent connections between the each pair of edges, each pair of vertices. So there are n choose 2 edges possible, and you know, if C, so you have this gauge, if C over n is such that C is smaller than 1, actually the largest connected component has size big O of log of n. When C is larger than 1, the largest component size already appears. It has size of order n. So you know, a visible proportion of the vertices is in there. And then at the transitional, you know, critical level, so this is here, when C equals 1, something unusual happens, and combinatorists studied this since late 50s, so in the 60s, 70s, 80s, and so on. They realized that the size of the component, of the largest component, is on the order of n to the 2/3. And then they realized that the second largest component is also of the size n to the 2/3, and the third largest and the kth largest. So something unusual was happening, and that's the, you know, the critical transition phenomenon. And okay, so now we move 20 to 30 years into the future, but I call the result still classical because it's been, you know, 20, 30 years ago. And so I was at that time at Berkeley, as Professor Jakubowski just explained, and my thesis advisor proved a remarkable result about the scaling limit. So not only is the critical phenomenon happening at 1 over n, but in fact, there is this critical window, and I'm using color coding. So lambda, this violet lambda or purple one, is this little, okay, so it's a real parameter. It could be negative or positive, but this lambda over n to the 4/3 is this little amount that you could move to the left or to the right of 1 over n and still see a critical phenomenon. This is what I just explained. So if you run the random graph and think about the connected components, and you rescale their size by n to the 2/3, you look at the largest one. So they are ordered in this non-decreasing order. You look at the largest size, the second largest size, and so on. There are only finitely many sizes because for any finite n, there are initially finitely many particles, and then it goes on. I mean, there are fewer and fewer components as time increases, of course. But anyhow, the n is larger and larger. And when you rescale the sizes, there is convergence in the best possible way. So, okay, you know, the usual convergence in distribution, that's the best possible with respect to the L2 norm, because the limiting object is actually, its natural state space is L2 without L1. So the total mass has to go to infinity. That's easy. I mean, that's obvious. But the L2 norm of the mass is stable. And we now call this limiting process the standard Aldous multiplicative coalescent. In fact, it is a process that I will discuss a little bit later. I'll tell you a little bit more about. For now, you just need to know that this little parameter lambda appears as a time. So it's the time of the multiplicative, limiting multiplicative coalescent. And okay, so I think I told you in different words whatever is on the slide. I hope you can see my and read my writing. You can see it, but I hope you can read it. I hope it's fun while I'm talking. And okay, so here's something that, so it's a key beginning of the Aldous's work, where, it's kind of a very clever little idea to understand that Erdős-Rényi graph can be just constructed in continuous time, so that every skeleton, when you stop it, so you run some process in continuous time, and it is the process where the edges appear at exponential rate. And if you stop, every snapshot is a random graph at a particular p. And the exponential rates are good because, exponentials have memory less and other nice properties. And basically you have a nice Markov process of components merging together in continuous time. And so these x1, x2 in the case, and the others, right? These little x's are the masses. So for the Erdős-Rényi graph, we had n vertices with mass 1, but this is what it says here. But you could, in general, attach to nodes arbitrary positive mass. Here it says bigger or equal to 0, but it's not interesting when it's 0. And so you attach them positive mass, and then the most important thing is that these exponentials have rates which are multiplicative. And okay, little thought is needed to see this. When you start with one mass 1 at every vertex, if you have, maybe I have a slide on that, let me see. If you have a component, yes, okay, so this is a slide about that. So start with mass 1. If you prefer, let's restrict to the random graph. So here we have mass 1 at every side. And then at some point we have a component, connected component, imagine many edges of size x, meaning of mass x. And here's another one, connected component of mass y. And kind of a beautiful thing, and the main thing that allows us to push the analysis through is the fact that these two components will merge at the minimal time of an edge connecting one vertex from here to one vertex from here. And if there are x vertices in here and y vertices in here, there are x times y possibilities. So we get the exponential, it happens at exponential x times y. And now I'm asking you to imagine a process, and it's true, such a process exists, where you have many, maybe even infinitely many connected components put in some space. It's not a geographic space, there is no distance between them, but you just kind of line them up. Maybe you put them in mass decreasing order in some, but okay, I always imagine it graphically. So you have them somewhere, and you imagine interaction where any pair merges at rate, any pair of components merges at rate multiplicative in their masses. So there is this rate x times y, and this happens all the time. So you have, in principle, okay, then you ask yourself, okay, can I do it with any kind of infinite vector of masses? No, you can't. I mean, you can, but you will get very soon infinity 0, 0, 0. So this is the kind of collapse that you don't, we would not like. But if your initial vector is in little L2, then the evolution will be stable. So if this merging happens, and in every finite open interval there are infinitely many mergings, this does not bother you, because the process will stay in little L2 at all times. Okay, so that's the point of this slide. Okay, so I move on. This is an interesting result. The famous proposition 4 in Aldous' paper, for everyone that works in this area, and there are quite a few people that have joined over the years. I'm a recent return. For a long time after my thesis, I wasn't working on multiplicative coalescent, but I returned maybe 5-6 years ago, and I'm happy about it. So this is about, just to show you that the scaling limit that Aldous obtained for the near-critical Erdős-Renyi graph is actually much more general. So there is a universality class of initial states, and there is a very precise set of hypotheses that are relatively easy to check. On the second moment, initial second moment, blah, blah, whether the largest component with respect to the second moment goes to 0. And this is the third moment, we call it the third moment. And what is the connection between the third and the second moment cubed? And if this is satisfied, then you have the same scaling limit of the multiplicative coalescent, these pre-limiting discrete state space continuous time to the eternal version, which we call standard Aldous multiplicative coalescent. Okay, okay, this is a slide about how, so just checking the orange thing in here, but I don't think I have time, so I put it in orange what it means for the random graph, where every vertex has size 1, and then this is a careful computation that indeed checks, here it is useful to actually divide the mass initially by n to the 2/3, and that means that you will need to, in the scaling limit, because now the masses are small and you need to wait n to the 4/3 time units more to see the critical behavior. Then the critical time is now of this kind, n to the 1/3 plus the lambda, the real time, and this lambda becomes the coalescent multiplicative coalescent time. And so this is a little slide about something that was, puzzling many people 25 years ago, 27, but now the process here in yellow is visible, and people are used to see it in a number of talks by my peers who like it. So it turns out that the characterization of the standard version, which exists at all times, it has this funny property that it is not a Markov process, it's rather an entrance law, because the second moment vanishes at time minus infinity. So you don't know how to start it. Well, you can start it by Kolmogorov extension theorem, but there is no way to start it with a transition kernel. And anyhow, at any fixed time lambda, the excursion, the law of x star equals to the law of the ordered excursion lengths of this Brownian motion with parabolic drift. And the lambda in the coalescent is seen as the drift as a parameter in the drift, in the linear part. Okay, So this was classical. This may not be viewed as classical, but it certainly, made a large impact on my life as a scientist, as a mathematician. There could be, on a graph, there could be some imperfections in the sense that certain vertices, or it could be a network, then it's called maybe a network, you have inhomogeneities, and the kind of basic inhomogeneity would be that while most of the edges appear at with probability p, or rather most pair of vertices are as in the standard Erdos-Renyi graph, certain pairs like each other much better, and maybe they are already connected. Okay, and of course so it's a perturbation of the vintage model, and of course as probabilists we know that small perturbation doesn't change much, and large changes too much. And so the question is, what is a perturbation which changes something, but maybe not too much, and you still have a interesting behavior. And here's a relatively how do you say, it's again a sketch, but a careful study of the perturbation that you might have. So there is this I special in this set of indices, a set of size, of certain size, and say that they're connected initially. You still have n particles. This set is small with respect to n. In fact, it should be small with respect to n to the 2/3, because the scaling, is such that, well, you should not be able to see it when you rescale by n to the 2/3. So relatively small set, but if it's too small, there will be no impact, in the sense that the scaling limit will be the same. If it's a little bit larger, there may be an impact, and if it's too large, everything will collapse. And it turns out that the right size, so the kind of critical good order size for us to see something new in the scaling limit, is n to the 1/3. And I'm already moving here into the continuous time. Okay, and maybe I move to the next slide. And here I'm discussing already, so there is a case of too small, of too large, where everything collapses. And I know they're small and large just because that I know what is the middle. So the middle is, suppose a subcase of the middle, that the special vertices form a set of size alpha n to the 1/3. And then it turns out that if you do everything the same, so you have these red edges that arrive between any pair, but actually you have, say, green connections. Maybe it's a complete, maybe it's a clique, maximal clique, maybe not, but okay, this has been previously connected. And if you let the space and time scale in the very same way, then in the limit, there is a new process. And okay, this new process is similar to the old one, somewhat similar. So it's a new coalescent, it's a new eternal multiplicative coalescent version. And this one is matched, or can be matched to the following process. So it's a parabolic, Brownian motion with parabolic drift, plus a jump. And this one jump corresponds to this alpha, and this alpha can be seen here. It's the proportion, coefficient alpha times n to the 1/3. You see an alpha here, and this psi alpha is also exponential of rate alpha. And it turns out that if you draw the excursions above past minimum of this process, reflected above past minimum of this process with the jump, and you again order them by their length, then it has the same law as this new process. Okay, so I already said that, it was my thesis. It was first done, in great generality in my thesis, and and also the paper with Aldous. And then I returned to this phenomenon for a different reason that I won't tell you now in my Bernoulli paper in 2019. Actually, I wrote it in 2016, but it took a while to get published. And so here, this is an interesting slide, but also on old stuff. Anyhow, I wanted to, I think it's important to try to explain that this new process, so the scaling limit, can be obtained via color and collapse scheme from the old process, old limiting process. So old one is the classical, the standard multiplicative coalescent, and this is the one where there was this part of community which preferred themselves. So they were already connected. So there was this, okay, so here I redrew this graph in a different way, already dividing by n to the 2/3. And so now I see there is a blob of size alpha over n to the 1/3. And then there is all this other stuff that is disconnected initially. So all the other vertices, and then they have there is this many of them, but it's the same order of magnitude. There is n of them, okay, minus something. This something is here in this small mass. And so this is sort of macroscopic dust, and this is microscopic dust. And a very important property that we have in these kinds of models, and everybody that works on them knows it, is that we can account for edges we can check for edges in the way that we like. And also, if we check for connected components, and so, for example, the way I like to do it here is to first analyze the blue. So these initially equal vertices, so all of them were of size 1, or rather of 1 over n to the 2/3, and then connect all the edges here and see what are the connected components. And then it turns out that, okay, well, we already know that this converges to the standard version. Well, this will not bother us. Okay, so this converges to the standard coalescent. And then I will account for the brown edges that go from the large dust particle to the small ones. But I can rely on the very important property that there is a persisting multiplicative coalescent. It's kind of related to the fact that I was mentioning, that we indeed have multiplicativity in the rates. So I can view each of these dashed edges separately, or maybe I can collapse the component and just say, okay, the edge between, there is a probability. Okay, so this is a new slide, maybe here. So the edge between this guy and, say, this connected component arrives at a multiplicative rate. And this is what I'm going to use, in fact. So here on this, on the left, there is scaling limit, which we know. I told you that it's x alpha of lambda. And here we put everything, we go to the scaling limit. Here is the standard version. And this actual mass goes to dot because it's a green dot of size 0, right? The mass of this is 0 in the limit. Okay, but this green dot has an impact. Maybe it's a dot in the mass, but it has an impact in these guys actually being connected via, in the pre-limit, they may be connected by both being connected to the green. Okay, so and here I'm actually computing connection of the green to the limit of xi, so to the green dot. It should be the limit of the the limit of the discrete, on the discrete, on the nth level, I wait for this much time. So this is n to the 1/3 plus lambda. There is the mass of the first one. There is the green dot still has mass on the nth level, small mass. And then there is the mass xi, and so the ith largest connected component at level n. And what happens is that this time n to the 1/3 and this n to the 1/3, they cancel out, and I get alpha times this. alpha times the mass in the limit. So n goes to infinity, this converges to the ith largest mass in the standard version, and this converges, the rest converges to alpha. So it is as if I was putting a green dot in every cluster, every component of the standard multiplicative coalescent, actually some point process of green dots, and I was checking whether, so this is the probability that there is no green dot in the ith component. And so everyone that gets at least one green dot gets connected to the green. So this is the point of this picture. And so now you understand that what I told you about the green color could be done by carefully, arranging. Maybe there is additional blue, and therefore I would have to have alpha 2 over n to the 1/3 dust, macroscopic dust particle. Maybe there is a third color of size alpha 3 over n to the 1/3. And in the end, the scaling limit would correspond to placing colored dots, Poisson point processes per unit mass with respective rates, and then interconnected everyone that has at least one color of the same, at least one mark of the same color, and then making the connection afterwards. So that's the color and collapse mechanism. And finally, I made it with all the delays, but I still made it to the new, so now I make a cut. There is something recent that we managed to do with a young collaborator of mine by the name Vitaly Konarovsky. It's an old model. It has various names in the literature. One of them is stochastic block model, and I'm showing you the most trivial, still non-trivially different variant from the Erdos-Renyi graph. So the idea here is that, and actually this model is also in many talks in this meeting being studied and work, but also by statisticians and probabilists. So the point is here we have a large number of vertices, and maybe they're all of size 1. Okay, so they're all equal, but they're distributed in classes. And here, actually, there are 2 classes, and they have the same size. In general, they may not have the same size, but they have large size, and it's going to infinity. And here there is this matrix P, which is analogous to little p. And here is the small difference is that the red edges, which appear within the classes, so I call them intra-class connection probability. Intra-class edges, they appear with little p, which is intra-class connection probability, while the purple edges, they appear with probability q, okay? And so here the number of classes is m equals 2, but in general, you may have many, many classes. And so it's already a network. And so our approach is similar to the multiplicative setting, to the Erdos-Renyi classical setting, where we will continuize, so make it continuous. We will have red edges which arrive, initially at rate 1, and purple edges which arrive at a different rate. And we think that this rate is much, much smaller than 1. And we will discover which rate this is. And then very soon after, I decided, no, let me rescale the masses so that each vertex has now mass 1 over n to the 2/3. And then let me say that within each class, there will be the multiplicative coalescent, so that the red are appearing now at rate n to the -4/3. Actually, you have to wait a long time until you see any particular red edge. And the purple is now also rescaled. So there is the same QN. Yes, there is an additional multiplicator. So it appears even more rarely. And we are trying to find a near critical regime and trying to find a scaling limit. And one of the questions is, what is QN? So here I already told you what I just, okay, this is great. So now you see an image. So we are thinking about the same critical time, so a critical window, and to the 1/3 plus lambda, which a parameter in real, parameter, real number. And so we do the same old trick. So very important property is that I can first think of the red edges. So let's see what happens class by class. I let it evolve, put them into the components. So okay, it is usually nastier than what I drew here, but here I pretend that I reorganize the edges, the vertices, so that the components are here, connected components. So this is the blue class and this is the green class. They're already connected components. And then afterwards, I will, so this is, can first consider the red and then form the connected components, and then we can account for the purple. And the purple edges, remember, they go only from class to class. So they are interclass edges. And the very important property now is that this is not a true multigraph, even though we see these purple edges. We recall the important property of exponentials. And how many minutes do I have?
-3.
-3, I already went. Okay, so so it is not a multigraph. In fact, there is a certain, I will be done soon. Okay, let me just finish this slide and the next one. So there is this connection that actually happens at the thick purple edge on the multiplicative rate, rescaled multiplicative rate. And so there is this theorem with Vitali-Konarovsky that already appeared in EJP, where we actually understood what is Qn. Qn has to be of this order, and we understood what is the limit, and the limit is something like the coloring. It is not quite the colored process. It is, if you take the standard, so these are the so within each component, there is, the limit is going to be the standard multiplicative, within each class, the limit is standard multiplicative coalescent. So this is standard multiplicative coalescent, the limit of the first class. This is of the second one. And the second one acts, okay, rescaled with this parameter S on the first one as a color, but it's not, it's a color with its mass. And then, I mean, you need to account for, it's a slightly different. Okay, I lied, maybe one more slide and then I'm done. So just to show you that we revisit the color operator, we revise its definition. Before, there were these green, blue, purple, and so on, the colors with mass 0, so trivial mass, and you didn't account for them. Now the color has mass, and once you color and collapse, you also need to add this extra mass to the system. And then that's what we call the interacting multiplicative coalescence. There are more complicated processes than the multiplicative coalescence. And yes, I think it would be a good time to stop because of the constraints. But if you wish to see the whole talk, I mean, the whole thing that I prepared, send me an email. I would be happy to distribute it. And thanks for letting me finish at a good place.
Thank you.